Okay, so welcome to this final video on quadratic forms. As announced in the third video, there is a discussion of case number 2, which I refer to as the J statistic case. Still, we are interested in the distribution of a quadratic form that involves a normal vector x with the mean 0 and variance covariance matrix sigma. So we use that quadratic form, x prime ax. The question is, under which circumstances does it come out as a quadratic form? And as before, we resort to the property of the multivariate normal distribution in the sense that we can trace it back to a vector of standard normally distributed random variables u, which are also independent as indicated by the identity variance covariance matrix. That is, we can write the quadratic form in a slightly different way, invoking this standard normal vector u and defining the matrix A tilde like that. From the previous video, we learned that such a quadratic form, which involves standard normal variables like u, this quadratic form comes out as a chi-square distributed random variable if the matrix that we use to construct the quadratic form, here the A tilde matrix, is an idempotent matrix. And the rank of that chi-square distributed random variable, the degrees of freedom of that chi-square distributed random variable is equal to the rank of A tilde. Now, in case 2, as a matter of factly choosing the pseudo-inverse of the variance covariance matrix sigma for A ensures that A tilde is idempotent. We saw that in the previous video. What remains to be seen, though, is what the rank of A tilde is. In other words, what the degrees of freedom of the resulting chi-square statistic is. So what is the rank of A tilde, or in other words, what is the rank of B prime AB? Well, A tilde is a P by P matrix, and there is no reason that this matrix should not be invertible. So the rank of A tilde should be P, but we like to relate this rank of A tilde and the degrees of freedom of the chi-square statistic more to the properties and the rank of the variance covariance matrix sigma. Okay, and that's what we're about to do. Okay, so in order to find out what actually the degrees of freedom of this chi-square distributed random variable which results from this quadratic form is we need to take a closer look on the construction of the pseudo-inverse. So far we just took a look at the properties of the pseudo-inverse, but not at its precise computation. And that's what I want to do next. Now, again, what is helpful is to consider a spectral decomposition of the variance covariance matrix sigma. Well, that's still a symmetric and square matrix, as any decent variance covariance matrix is. And for that symmetric and square matrix, we can employ a spectral decomposition, like this one. The point is, in the present context, some of the eigenvalues that we collect in the matrix, in the diagonal matrix lambda, are 0. Okay, so maybe you want to take a look at how lambda looks like in the present context. We will have these non-zero eigenvalues on this main diagonal, but then comes some zero eigenvalues as well. Okay, and that fact is responsible for the non-invertibility of sigma, for its singularity. So that's a spectral decomposition as usual, and as in any spectral decomposition invoking a symmetric and square matrix, we will have the result that the eigenvectors collected in the matrix C are orthogonal, and this means that if we compute C, C prime, or even C prime C, we get the identity matrix. And also recall that C prime acts as a inverse in the case of a symmetric and square matrix. Now, for the construction of the pseudo inverse, what we do is we collect the non-zero eigenvalues so these would be lambda 1, lambda p, and we write them in a diagonal matrix. Okay. So here comes lambda 1, lambda 2, lambda p. The remainder of the matrix is filled with zeros, so we call this diagonal matrix big lambda 1. And moreover, we collect the eigenvectors that correspond to those non-zero eigenvalues as well. Okay, and these eigenvectors are collected in a matrix which has in its columns those eigenvectors. So each of these vectors is an n by 1 vector, and they are collected in this n by p matrix, and we call that matrix big C1, and that's an n by p matrix. Okay. Now after this collection, we can compute the pseudo inverse, or more penrose inverse, or generalized inverse. And this matrix results from taking the eigenvectors in this kind of a spectral decomposition and have the inverse of the lambda 1 matrix in the middle. And this is how we compute the pseudo inverse. Now, what the pseudo inverse should deliver is the following property. And we can check that actually this computation delivers what we want it to deliver. We said that one of the properties of the pseudo inverse that if we multiply it with sigma, multiply the pseudo inverse again, we should get the pseudo inverse. And moreover, the property that if you take sigma, multiply with the pseudo inverse, multiply with sigma again, we get sigma. So these are the desired property of the pseudo inverse, and we can check out that this is actually true, and we can check it out for this condition. We can verify it. So let's insert the concrete computation of the pseudo inverse in the expression. Okay, that's sigma plus. We need sigma, and I use the spectral decomposition of sigma for that purpose, and I have sigma plus again. Okay, and the claim would be that this is equal to sigma plus, that is C1 lambda 1 to the minus 1 C1 prime. Oh, excuse me, I just noted that there is an error. That should not be a prime here. The prime should actually go here. So please correct that mistake. Okay. Right. Now, we can verify that this claim actually is true by taking a closer look into the components of the left-hand side expression. So we would have C1 here, which we leave. Lambda 1 to the minus 1 is the inverse of lambda 1. Lambda 1 is a diagonal matrix, and the inverse of a diagonal matrix is easily computed by taking the elements on the main diagonal and inverting them. Okay, that's lambda 1 to the minus 1, and now I like to write here actually C1 prime C. So the result of that operation. And to understand what's going on here, we should remember that the eigenvectors of the symmetric and square matrix are orthogonal to each other. So if you take the inner product of one eigenvector with another eigenvector, out comes 0. And if you take the inner product of the eigenvector with itself, out comes 1. So we norm the length of the eigenvectors to be 1. In other words, the eigenvectors, the matrix of eigenvectors is orthonormal. So if you carry out this operation, C1 prime C, we see that sometimes you multiply the eigenvector with itself, its inner product. Sometimes you multiply an eigenvector with another eigenvector, and we end up with a 0. So the result of C1 prime C is then a matrix that looks like this, right? You can write it in the following form. We have a matrix that has 1s on the main diagonal and 0 off. So that would be the p columns of that matrix, kind of an identity matrix of order p that we have here. But then there's also some columns of the matrix which contains zeros. Okay, that's the result of C1 prime C. Try it out yourself and see whether you get the result. Then we would have lambda, and we already had lambda before. So lambda would be a matrix that contains first the non-zero eigenvalues, then come those zero eigenvalues afterwards. Okay. So again, have this subset of p rows and p columns. Here are zeros. Here would be zeros. Here would be zeros. That's how lambda looks like. Okay. Then we would have the matrix C prime C1, and you see that this is just a transpose of that matrix, right? C1 is the transpose of C1 prime C, so we can write the transpose of that matrix, and that would look like that. I have 1s on a main diagonal, 0s off, and then I have some rows of that matrix which contains zeros. Okay. So here the last rows of that matrix would be zeros. Essentially, these are the transposed last columns of that matrix. Okay. Then comes lambda 1 to the minus 1 again. We already had that. So I'm writing it again. That's lambda 1 to the minus 1. And then finally we'll have C1 prime again. That's a detailed expression of the left-hand side. Now, the thing to note is, if you take a look at these terms and multiply them, what you actually get is lambda 1. So you get this matrix which contains on the main diagonal the non-zero eigenvalues. That would be a p by p matrix, and if you take this matrix and sort of post-multiply it with that matrix, you immediately see that you get an identity matrix out of it. So this is why a lot of terms cancel out, and you are left then with the term on the right-hand side, And that is the claim, right? If you carry out this multiplication invoking the pseudo-inverse of the matrix sigma, you should get the pseudo-inverse again. And this example here verifies that it actually is true. Okay, so that's just a sidetrack to illustrate a bit the computation and the use of the pseudo-inverse. And now we want to make use of the pseudo-inverse and the formulation of the pseudo-inverse using the eigenvectors and the eigenvalues. And we use that for the present context. We had this matrix A tilde, which was written as B prime sigma plus B, in our context the P by P matrix. And now let's write the right-hand side expression using the definition of the pseudo-inverse. So I have B prime C1 lambda 1 to the minus 1 C1 prime B, and we can take a look at the dimensions of the matrices which are involved here. So that would be P by N, that's N by P, that's a P by P matrix, that's a P by N matrix, that's an N by P matrix. Okay, and remember, ultimately what we're after was we were interested in figuring out the rank of alpha tilde. Right? That's where we started the whole exercise from. And to figure out the rank of a tilde, it's now helpful to take a look at the right-hand side expression, because we can figure out what the rank of a tilde actually is by using, again, the product rule. We had the product rule already, and the product rule is applied to the product of three matrices A, B, and C, and we are interested in finding out the rank of the resulting matrix, and this rank happens to be the rank of the matrix in the middle if A and C are non-singular matrices. Okay, and we can check whether the applicability of the application of the product rule in the present context is going to give us some idea about the rank of A tilde. Now here, what we have is our A matrix in the present context would be B prime C1, and the C matrix would be C1 prime B, right? And as a matter of fact, both matrices are of rank P, and these matrices are non-singular. Okay, they are both P by P matrices, and they are non-singular. Okay, so maybe we'll write the dimension here. I'll write the dimension of these two matrices, and there's no reason that these matrices should have some linear dependencies built in. They should be a full rank P, such that the rank of A tilde is then determined by the rank of lambda 1 to the minus 1. Okay, so the rank of A tilde is then the rank of, writing out the matrix again in detail. Okay, and by the product rule, that would be the rank of the matrix in the middle, that is the rank of lambda 1 to the minus 1. That's a diagonal matrix, and the rank of this lambda 1 inverse is the same, of course, as the rank of lambda 1. But remember that lambda 1 contains the non-zero eigenvalues of sigma, and this is precisely what the rank of sigma is, right? The rank of sigma is the number of its non-zero eigenvalues. And these non-zero eigenvalues are precisely what we actually collect in the matrix lambda 1. Okay. Lambda 1 contains these non-zero eigenvalues on its main diagonal. Okay. And now we can conclude that the quadratic form that we're interested in, right, X being normally distributed with mean zero and variance covariance matrix sigma, but with a sigma that is not of full rank, there are linear dependencies in X, that this quadratic form is a chi-square distributed random variable, and now we know its degrees of freedom. The degree of freedom is equal to the rank of the variance covariance matrix sigma, and that shows result 2b for case number 2, that is where sigma is not a full rank and where we have to use a pseudo inverse to construct the quadratic form. Okay, that is essentially what I wanted to show. Now maybe as a final conclusion, we can verify that we actually have shown the distribution of the limiting distribution of the J statistic. Right? Which is what we originally wanted to show by the whole exercise. Now, let's collect some early results. The sample averages evaluated at B hat and blown up by square root of t converge in distribution to a random variable x that is distributed normal with mean zero and an asymptotic variance covariance matrix that we have denoted like that. Okay, and we may, in a shorthand notation, say, okay, this is our sigma, right? This is our variance covariance matrix, and we immediately see that, hey, this X matrix has exactly the properties that we wanted to have. It has a mean zero, and it has a variance covariance matrix. Now, it turns out that this variance covariance matrix, sigma, is of rank n minus k. A GT, that's an n by 1 vector, but the variance covariance matrix is per construction not of full rank. This is actually what we have shown in the first video. Okay. Secondly, what we did is we used a quadratic form to construct our test statistic. This quadratic form looks like that. We take GT of B hat, transpose it, take the pseudo inverse of an estimate of the asymptotic variance covariance matrix. So that thing would be the asymptotic variance covariance matrix, GT B hat, estimated, and we take the pseudo inverse of that object. That's the thing that we use for the quadratic form. Square root of t gt b hat again. Now, by one of the lemmas that we've taken from Hayashi, which is precisely concerned with the convergence of such quadratic forms, we learn that this random sequence converges in the distribution to x prime sigma plus x, noting that we actually are able to provide a consistent estimate of this pseudo inverse, and we can, if we're able to provide a consistent estimate of the asymptotic variance covariance matrix of GT of B hat, and suppose we can do that, then we find that we have this convergence of the quadratic form to this term, which is a quadratic form, of a type that we've just studied, right? It's exactly what we have. X being normally distributed with mean zero and a non-full rank variance covariance matrix. And the point is, we now know what this quadratic form has. What the distribution of this quadratic form is. It's a chi-square distribution, and now we also know what the degrees of freedom are. The degrees of freedom is equal to the rank of the variance covariance matrix sigma, and this rank, as we show, is n minus k. And that shows again the limit distribution of the J statistic. Okay, and it's very important to know that distribution, because as we've seen, the J statistic is extremely important for testing the validity of moment conditions, and in our context of testing the validity of the model. Okay, so that's it in terms of derivations surrounding the properties of quadratic forms, and in particular their use for the construction of the Wald statistic and the J statistic. Okay, so thanks for watching. Again, if you have comments on the videos, maybe if you've spotted an error, please contact me. Thank you and goodbye.